All right, hello everyone. I'm Zoe Blevins. I'm with the network automation team here at Yahoo, and I'm here with Yuahe from the architecture team. And we're here to talk to you about the automation that we've developed to automate our class networks. So unfortunately, I'm here presenting with a broken wrist. Fortunately, we designed our system to be hands-off, so.
I'm the clicking monkey.
So what we're going to do is talk about our motivation for developing this system, the components we developed to make it happen, walk through a specific use case that's handled by the system, and discuss our results and future applications.
So I guess our talk is just too boring, so I have to flash you a picture. So this picture is probably the first public appearance of our class network. So we have been running it for a number of years, and so it was implemented, designed, and prototyped by our network team and the data center team. So kudos to everybody who has involved.
All right, so let's talk about why we need this level of automation. Obviously, class networks have pretty elaborate topologies. They are pretty complex, and they're just not manageable without some sort of automation. And so a lot of people will start with automating the initial state, generating those configurations and having the engineers push them out to get the state where they need it to be to start. Problem with that is networks aren't static. We're constantly making changes, and asking engineers to constantly be regenerating configs and pushing them out to the network can be a hassle. Additionally, configuring the devices isn't just a matter of reflecting the desired state. We do need to get in some of those current state pieces in order to develop a cohesive configuration for the network. So the solution that we came up with was to design this system around state machines so that way we could track the progression from our current state to our desired state.
Yeah, so before we go any further, so I just would like to mention two observations that I think that is important in leading to the solutions that we are trying to propose in the next few slides. So the first observation is there's always two states in any of the systems. The first one is your desired state, the system's desired state, and the second one is actually your current state. So these two states are not exactly the same, and often they are different. And the process of actually the action of pushing the configurations into the devices are actually a process that try to reconcile these two states. That's the first observation. And the second observation is that we actually have to have the system actually has to take into consideration of the live data. So what I mean live is that the current system that, for example, if you have packet losses in a certain link, that the system may have to make decisions upon that to put whether routing protocols are on that link or not. So those two observations lead us to the decision of using a state machine and as well as a tight control loop in order to generate the next, the desired configuration state. So we'll go next.
Yep, so obviously the first thing we need is to establish that desired state. The way we did this is that one nice thing about the network we architected is that we designed it with automation in mind from the beginning. So we actually developed it alongside a model of it, and that model is what we use to dictate that desired state. And that model deterministically defines things like our IP addressing, our topology, what we advertise out. And all of that is actually defined as soon as the cluster is created. So at the time anything's plugged in, we know exactly the IPs it's going to get, we know exactly where it should be plugged in, and all that good stuff. But it's not enough just to say the state that we need on creation. We also do have those changes I mentioned, so we do take in inputs from our network engineers into the model. Those inputs can be some things like new host subnets that we want to advertise, configurations for the Tor host subnets, and then the generic cluster level settings, things like auth hosts, log servers, NTP servers, all that good stuff. So as we mentioned, we do need that current state as well. So we developed a live state telemetry gathering system. And what this does is we have live metrics and metadata that are sent to our collection system every 30 seconds by agents on the switches. And these are used to calculate our port state so we know what type of configuration changes need to happen, and it also allows us to monitor the system health. The metadata is actually used for tracking the advancement of the config delivery system and also in a few pieces of our config generation system. So by having this system, we can allow, by having the live state telemetry, we can allow our system to react to real-time changes on the network. So we also, as I mentioned, we use these device agents to push these metrics to the live state system. So the way the agent works is it actually has two functions. It has the metric gathering, and it also has a config application system. So as I mentioned, the metric system posts to our live state collection system every 10 to 30 seconds, and it posts things like link and admin state, LLDP neighbors, input-output rate, and some other data we have in there as well. And then we also have the config application portion. So what this does is when our system has released a config to be loaded up, the switch can reach out to a location and load that configuration file over HTTP. The agent then performs the config replace and runs health checks to validate that the config was applied as expected. And those health checks include things like the actual success of the config replace, it didn't throw any errors when trying to apply the config, validating that we have our default route and that we haven't seen too drastic of a change in prefixes received and advertised, as well as some ping checks that we do. And there's additional health checks to this, it's just kind of a sampling. What this then allows the system to do is automatically perform a rollback and report back if something did go wrong, and then a network engineer can get involved and resolve it. I do want you all to kind of comment for a moment on why we went this route instead of some of the open source solutions for getting configs onto devices.
Yes. So we actually look at the way that how we actually want to do the config pushes and the way that the system, how they actually are interconnected, and then the configurations are actually interdependent with each other. And then the fact that it actually has to take the live data in. So the off-the-shelf solutions that we feel that is not easy to actually incorporate into these scenarios. That's why that we will actually lead to here in the solutions that we present here.
Great, so we've got our live data, we've got our desired state. We now need to morph those into something we can push to the devices. So obviously the goal of any config gen system is to produce a config, but as I mentioned, we do need to get that live state in there. So our config gen system takes in several inputs. It takes in our network model, so that's our desired state. It takes in our live state. It also references some of our external data sources, things like our asset management system, our IPAM system, et cetera. And it then populates our device templates. So we happen to use Apache Velocity in our case, but Jinja 2 would also be a great solution for this. But it's not enough to just have those inputs. We don't want our engineers to have to say, hey, system, go generate a config. We want that to happen automatically anytime a relevant change occurs. So we created a set of triggers that cause a new config to get created. So those triggers include things like the initial cluster creation, when we allocate new top-of-rack switches, any port state changes that we detected from our live state system, as well as subnet changes and template changes. So that's all well and good, but we do need to get that config out to the devices. So the goal of this system really is to release those config changes rapidly, but also in a really controlled manner. We don't want to blast out a bad config and take out an entire cluster. So we do have a lot of control built in place, and I'll touch on that a little bit later. So our solution here, this is kind of where that state machine comes in. We have three distinct states that a configuration can be in. It can be in the generated state, the release state, or the validated state. And these states are actually determined by comparing the config versions that we have persisted in the database. And by persisting that in the database, this means we can actually restart our system at any time with literally no impact at all. Each of these states are processed individually and in parallel, so they are asynchronous. There's nothing that's holding up all the switches in each state. There's no reliance on the previous states. So here's our state machine diagram, and I'm going to talk a little bit about how we process things at each state. So in order to get into the generated state, we get a config trigger. What those config triggers do is they set a flag in the database that flags that device for requiring a new configuration. Once that config has been successfully generated, the generated version is now incremented. So at that point, it's higher than the released version, which is then equal to the validated version. To get from generated to released, that's where that control mechanism comes in, and I'm going to cover that in depth in the coming slides. But once we are in the release state, the controlled release process increments that released version, so it now matches the generated version. And we are safe to write that config to disk to be served up by HTTP. So in the release state, we pull in all of those that have the matching generated and released versions, and we simply write them to disk. From there, that's where the device agents come in. Those device agents will check that path for a new config. It'll load them up, it'll determine what version it's on, and it'll report that back to our system. Once our system has seen that the version running on the device matches our generated and released versions, then we say we're in the validated state and we're prepared to generate more configs. So one thing I want to note is we do not allow any backwards motion through this system. You cannot go from released back to generated. We halt generation until whatever's been written to disk has been successfully loaded by the switch. This is so that we know exactly which config the switch will be trying to load up. We don't want to have things move backwards and cause confusion when troubleshooting.
Yeah, so I would like to add that this diagram is actually pretty important to us, and then both Zoe and I actually are often refer back to this state diagram. So basically, if you look at the state diagram of the validated, basically it represents a case that the desired state is the same of your current state, and the generated and the released state is actually represented the case where your desired state is deviated from your current state. And the state transition is basically just reconciling those two states. And the reason for us to actually separate generate and release is because that we don't want to blast the entire configurations to all the devices. We need to actually have a controlled release that we will be seeing in the next few slides. So. Yeah.
All right, so let's talk about this controlled release system. I think many of us would agree this is arguably the most important part of the system. We really don't want to propagate bad things. So what we do is when devices are in the generated state, they're sorted into two queues. And those two queues are based on the actual physical planes of redundancy in our cluster networks. So queue A contains all the switches in plane A, and queue B contains all the switches in plane B. These queues don't advance unless the health checks pass. So we get our generated devices into our queues ready to be released, but we also need to track our devices that are currently in the release state. So what we do is we sort those released configs into subqueues by device type, and we limit the number of new configurations that can be out at a given time in that release state. So when a slot in the subqueue opens, a switch in the generated state will then advance to the release state, but not before that happens. Additionally, queue A and queue B are mutually exclusive. So we cannot have devices that are in both queues in the same subqueue at the same time. We want to make sure that plane A succeeded before plane B switches get processed. So I have a diagram here to kind of demonstrate that a little more clearly. Let's say we have a leaf switch that was in the generated state and is in queue A. If the leaf queue is full, it'll wait until that spot opens. The spot opens when a leaf switch moves from the release state to the validated. So let's say we have a leaf in queue A and there's 2 leaf switches in queue B, and we allow, say, 10 leafs. This is actually a tunable value per cluster, so I'm just using arbitrary numbers right now. But if there were open slots, but it was a QB switch that was in that leaf subqueue, the QA switch cannot enter until all of those have cleared out, and then it can resume and move on to the release state.
Yeah, so I would like to just add that basically this is more like a TCP slide window where that you only allow a certain number of devices that enter this released state. So yeah. So obviously that's one of our major safeguards. We do actually have a lot of other safeguards in place for the system. So we do input validation on any model changes. We want to make sure that engineers don't typo something, don't flub something, and have it propagate out to the network. We also have a peer review mechanism for any cluster setting changes. We really don't want an engineer to typo an auth host IP and then suddenly we're all locked out of the network. That would be pretty terrible. So we do have peer review and validation in place. We also have what we call the big red button. And what this allows us to do is enable and disable the system at both the switch level and the cluster level. So this can be used in an emergency scenario where we need to just stop the system, get things to a healthy state again before resuming. But it can also be used for a couple other use cases. So if we are making some massive template change, we can actually use this to canary test those changes and roll them out a couple switches at a time, and then maybe a cluster at a time, and so on. We can also use this to prevent bad gear from blocking in those subqueues. So if we have a device that failed because of some hardware failure,
we don't want it taking up a slot in that sub-queue in the system until it's been replaced and healthy. So we would remove it from the system, and then we would insert it back in once that RMA went through. We can also use this for postponing changes until a maintenance window. So if we had an engineer that wanted to go ahead and make the change in the model ahead of time, and then just simply flip the switch when their CMR starts, that's an option we can do. Another layer we have is we do have a CLI on the switches that allows us to perform both rollback and shutdown of the system in case our model becomes unavailable for our engineers to access or something goes wrong there. They can still disable it at the switch level. And then, of course, we have our monitoring. I think that's pretty crucial here. We need to watch how our changes propagate through the network and alert if things don't behave as expected.
Yeah, so I would like to add that, so if we have to develop a totally safe system, that it would have to be two systems that are developed for the same purpose independently. So that's probably not quite feasible for us. So the next best thing that we came up with is to try to defend this system in multi-layers. So basically, we put safeguard in different layers of the systems at the control layer, at the control push layer, and at the device layer as well. So hopefully, one of those layers will catch any of the errors that we will be seeing.
All right, so here's some of the tasks that we've automated with this system. You'll notice that it closely aligns with those config triggers I mentioned, because any kind of network change will produce a trigger, and that's what causes these tasks to occur. So these are things like cluster creation, template changes, subnet changes, allocations, retires, and cluster settings. So let's walk through a specific use case. This is a pretty common one we have. And so what we've done is we've created a form that our system engineers can use to request a number of new TORs with a certain configuration. Once they complete that form, those new TOR switches are allocated both in our model as well as our external data sources. From there, those top-of-rack switch configs get generated and released, and the leafs that connect to them also get generated and released one plane at a time. So that's the stage where we're going through that state machine that we described. From that point, the leaf would load its new configuration. And the first step in that new configuration is actually unshutting the port. So we've got a TOR provisioned. We need our system engineers to be able to plug it in. So we would have usually a pause between steps 5 and 6. So the port gets unshut, it's ready to accept a device, and then at some point later, our data center engineers come in and they rack up that switch. So from there, the TOR would load its new configuration successfully. It would come up as a neighbor for the leaf, and they would see that they're both connected to the correct place, and the leaf would detect that as a port state change. From there, it would iterate through the processes, the steps needed in order to establish all the BGP sessions. So I am actually going to break this down a little bit further on the next slide. So we have kind of a secondary state machine. This is our port state change machine. And this specific diagram only applies to leaf to TOR ports. We will have different states for different relationship types. So we do have 5 distinct states. These states are unused, provisioned, connected, addressed, and routed. In the unused state, that means that we have no top-of-rack provisioned in that slot. It's shut, it's not doing anything. As soon as an engineer comes in and provisions something from the UI, that port gets unshut. And I actually included a config snippet here so you guys can kind of see how this works in the config. I won't go into that in detail, but you're welcome to take a peek at it later. So once the port gets unshut and our data center engineers plug in the top of rack, we'll see that the link state comes up, and we'll make sure that the neighbors match. If there was some mismatched cabling, we will not advance from provision to connected. We want to make sure that those neighbors are exactly what our model dictates. From there, we apply our IPv4 and IPv6 configs, and we verified that those came up successfully and that our packet loss rate is 0, so that link is healthy. At that point, once we get to the point where everything's healthy, there's no packet loss, we then apply our routing config. So once the routing config is applied, we verify that our v4 and v6 BGP sessions established as we expected, and it moves into its final state, the routed state, and that means it's fully configured. You'll note that these are all unidirectional. This is another state machine. We do not allow backward movement. We do not want to link to flap and then we rip out all the routing config. That would be pretty terrible. So at least in an unexpected manner. If we do some more live reactive stuff, we may plan for that, but we don't want it to happen outside of our control. So the only thing that allows you to go backwards in the state is a top-of-rack retire, and that process entails deallocating from our model, deallocating from all the external data sources, and then shutting that port and verifying that everything goes through as expected. So let's talk a little bit about the results of running the system on our network. So at this point, engineers aren't involved at any point in config gen or config deployment. They don't have to touch that at all. A lot of the common tasks can be handled by our systems engineers. They don't need NetOps intervention, so we can save our NetOps engineers for more important tasks. These switch config changes typically converge in about 30 seconds to 2 minutes, usually closer to 30 seconds. This is pretty rapid. And then cluster-wide changes can propagate in around 10 to 15 minutes. And that's something, as I mentioned, we can tune how many devices we allow out at a given time, so we can increase or decrease that as we see fit. So kind of the big point here is that we are now capable of provisioning a 20,000 node cluster in under 10 minutes with no errors. It just comes up, it works, it's great. So we do have some ideas of what we'd like to use this system for in the future. We can definitely expand this model beyond just our data center networks. And we also are toying with the idea of doing that self-healing that I mentioned based on these live state changes. We have the data, we might as well react to it. We can also do dynamic provisioning of host IPs. So the top of racks do report all of their neighbor data, including the hosts that are connected up. So we can get some of the data there and dynamically change our network that way, as well as doing some dynamic allocation for capacity. If we see that we're running out of capacity, we can actually we can skip the whole system engineer form, we can preemptively allocate those and just tell them, hey, here's a ticket, go plug it in. So that's all we've got. If you guys have any questions or concerns, feel free to come up to the mic or talk to us after. Thank you.
Yeah, so I would like to add that, so I would like to add that, yeah, we have pretty interesting problems as you have seen. So yes, if you are interested, talk with us as well.
Yeah, hi. This is Srinivas Raju. Hi, this is Raju from LinkedIn. I have a question over here.
Sure.
Is operational audit part of this particular tool? Like after you deploy, how do you ensure like the syslog entry is happening properly or not? Is the TechAxe working properly or not? Do you take care of this?
So this system does not. We do have other systems that monitor that, just external to this. This was very specifically the generation and deployment cycle. But yeah, we do have separate auditing tools.
Thank you.
Yep. Any other questions?
Can I borrow your microphone?
Oh, sure, absolutely.
This was easier than waiting for the roaming microphone. I'm Vince Cerf, in case anybody wondered. You should sit down now. It won't get any better than that. I have two questions. The first one has to do with configuration in general. I found this to be the biggest bugaboo of any kind of network operation because you can configure stuff wrong and it isn't obvious. So I'm just wondering if you had any secret pixie dust for detecting that a configuration is in fact wrong or non-functional or harmful.
So that's where those health checks come in. Obviously, that's not foolproof. You can't plan for every single failure, and that's why we have the big red button. If we do see that something's going wrong and our system didn't detect it as a failure, we can quickly shut down.
Okay, so the second question has to do with the ability to back out. You mentioned that you have a manual capability at each site, I guess, to command line interface that lets you. Another thought, though, that comes to mind is having 3 copies of the operating environment, if you like. The current one, the one that you're planning to propagate, and the one before the current one that will give you the ability to go back to perhaps a known state.
Yep. So we actually do have that on the devices. The devices store, I believe, a month's worth of, or we have a limit of how many configurations it stores, but you can restore any config version at any time. And then our kind of paradigm here is we actually really want to roll forward. So we do that rollback in emergencies, and then we fix the model so that the model can then again dictate the configuration. We can figure out what went wrong, and then we can update the model again to get to that state that we actually wanted.
So let me comment on more on that answer. So so basically the system itself, the config generation system is configured as the roll forward system only. So basically if you see any errors that you are supposed to change it from the source to make it work. Now, what if the system doesn't work, right? So we actually have another one, all the copies of the previous configuration stored locally in the devices. And in case there's anything that wasn't able to work, that you will be able to roll back to a certain point of time in the past. And then that has actually another automated system to actually to push those configurations or instruct the devices to roll back globally.
Just one other little observation. Generally speaking, if it was working okay, and then you rolled out a new configuration and it isn't working okay, it's nice to get back into a state where you think it was okay.
Yes.
And then try to figure out what went wrong. So I usually tell my guys, show me that you can get back out of what you just messed up.
Yep, correct.
Yeah, and that's, I mean, like I said, we have that in there for those emergency situations. We try to avoid it, but you absolutely do need it.
Oh.
All right, Igor?
Hi, Igor Yahoo, one of the architects of this thing. What Vin said obviously makes a lot of sense. Something that you have to be very careful of is if you, for some reason, are unable to roll forward, there's a high probability that you're also unable to roll back. So if I try to deploy a config on 1,000 switches, 3 fail to take it, I decide I need to roll it back, then 3 more fail to take the rollback, and now I'm in a completely unstable state. And that is why we actually control the number of devices in released. Because what happens is if X amount of devices, let's call X equals 3, fail to take the new config, I am better off pausing the entire deployment process rather than having a cluster in a complete set of unknown configs with an unknown redundancy model and no clue, like this is Rev 17, this is Rev 19, this is Rev 15, what's going on? You are better off pausing, at least from our perspective.
Great,
and
thanks.
then human will take manual intervention if need be to restabilize the system.
Exactly. Thanks, Igor.
Sure.
All right, any other questions? Yeah, well, thank you guys so much.